Welcome back, everybody, to What Do You Know with Nick and Devin. I am Devin.
And I'm Nick.
Thanks for being here, everybody. Nick, I have a question for you. Right off the bat. Bam.
Kick her off for us.
Starting strong. It's almost summer. It's summer-ish.
It's not, but sure. It's like a cool 36 out, so not quite summer, but sure.
Yeah, but it's almost summer.
Yep. Mm-hmm.
And, you know, summer, we get water parks open.
Yes.
Do you like water slides? Do you enjoy water parks, water slides?
No. But
okay.
I'm sorry, I got distracted because all I'm thinking is the jingle for the one water park. It's something fantastic. You know
was that not calamari?
No, that's Kalahari, not calamari.
Or you think of Great Wolf Lodge?
Great River Water Parks.
Oh,
Great River Water Parks.
Yeah.
Yeah. Mm-hmm. I got distracted by that. But anyway, I still don't really enjoy them. I'm not a big water person, and I also have to pause us because I feel like every time you ask me a question, it's always about something that I'm not into. I do have interests. I just want people to know there are things I enjoy.
Nick's the most boring.
Right.
He watched his paint dry. That's his opinion.
Just stare at my white wall when I'm sitting at home. I have a personality.
Yeah.
I like to have fun, but no, I'm not. I just it's not for me. Just any sort of. I enjoy the water, but no.
Yeah.
I'll stop there.
It's funny. I purposely ask you questions that I know.
Son of a bitch.
I have another great question for you lined up for the next episode that I do. So don't hold on to your seats for that, folks.
Don't go too far.
You got 2 weeks. So you don't like water slides?
No, I enjoy the thrill of it.
Okay.
But I don't like the water aspect of it.
Okay.
I'd rather a roller coaster than a water slide.
Oh, okay.
You know what
Fair.
I mean?
I wasn't sure if it was a public thing, being in a public pool issue.
That too.
That's understandable.
This is not meant to be seen outside of close. What do you call it? But there was one, I think it was when we went to Cedar Rapids.
Yeah.
They have a water park attached, and there's one body slide that you go all the way up. And I went down. I remember going down, and I came off of it, and I was like, "This is it. This is how I die." Because then I just imagined I would just tumbled forward and then just fall into my death. But Fair. It was fine.
Do you like the ones that was that the one that you just described? Was that a tube one?
Oh, it was open.
It was open. Do you like the open ones or the tube ones?
I prefer the open ones because the tube ones make me. It's not a claustrophobia thing. It's a
fear of getting stuck.
Fear of getting stuck or death.
Okay,
yeah.
that's
because
fair.
then if it collapses, you're stuck in the tube. You know what I mean? Okay. Whereas if it's open and it collapses, I have open air. You know what I mean?
That's fair. Mm-hmm. Fair.
It's a control thing.
No, I get it. I get that. And then my final question, I believe, is part of this bigger question, is do you prefer the thrill of going down the slide through the tube down the slide, or do you like when there's the crash of water? What's your favorite part of the slide?
Oh, in that, I think going down than the crash, because the down is the adrenaline. You know what I mean?
Yeah.
The crash is okay. It's over. You know what I mean? It's the adrenaline that I enjoy.
Yeah, the crash is the reaction, and you're like,
right. I'm an adrenaline.
The release of all the
junkie.
Energy happens at the crash of the water.
Correct.
Excellent.
But what about you? Do you like water slides?
I haven't been one. I don't know if I've ever been on a water slide.
How the tables have turned.
I know.
How the turntables.
No, we didn't go to a lot of water parks or public pools, really.
Fair.
We used to run the hose down the slide in the backyard, create our own water slide,
or slip and slides.
Yeah, slip and slides. I love slip and slides.
Slip and slide is great.
Done a lot of slip and slides.
You would just burn the shit out of your skin on a slip and slide.
Oh yeah, it was great.
And then just right into the grass. 100%. Okay, back to your topic.
My topic. So I wanted to talk about the water slides and going through the tube and the reaction because I wanted to ask, what do you know about particle accelerators?
I knew it had nothing to do with the topic. Absolutely nothing.
No, there is. See,
I'm sure
I did a tube water slide because a tube is part of the particle accelerator, and then you are acting as the particle accelerating down the tube and crashing into the water to get a reaction.
Yeah, you build that thin metaphor between the two.
I think it's a perfect, perfect metaphor.
What do I know about particle accelerators?
Yeah, please.
I know CERN. I know the God particle. I know they go very quickly, and there's a few of them throughout the world. That's it.
Oh, great.
Cool.
That's pretty good.
All right, thanks. I also just watched the three-body problem, so that helps with some of that information.
All right. Well, to start with particle accelerators, we are going to answer 3 questions.
It'll be 3, yeah.
What, why, and how.
Okay.
What is a particle accelerator? Particle accelerator, similar to a water slide.
I thought you were going to say, why is a particle accelerator?
I'm not answering these questions.
How is a particle accelerator?
It feels okay. You know, it's a little chilly out on Saturday. So what is a particle accelerator? It is a tube that shoots particles close to the speed of light.
Yes.
And the particles, once they are blasted and energized, then either smash into another particle flying in the opposite direction, or they smash into a stationary object.
Okay.
That's the what.
Got it.
Basic ass.
Basic ass what?
Why do we need particles to be accelerated that fast?
Yes.
I get really excited and I just hold in all of this air.
It's okay. I also have like 18,000 questions, but I'm like, let him do the topic and ask at the end.
Feel free to ask throughout.
Okay.
So why do we need particles to be accelerated that fast?
Yes.
There are surprisingly many more uses for a particle accelerator than just the joy of smashing shit together.
I love that.
Obviously, there's the study of the world of the infinitely small and other purposes to research nuclear physics.
Sure.
There are also many medical uses, including sterilizing equipment, producing radioisotopes used in pharmaceuticals for cancer diagnosis and therapy. And then larger accelerators can also be used to destroy cancer cells. So we just like shoot particles at your cancer cells.
Oh, I love that.
Yeah.
I have a question.
Thank you for raising your hand. We'll see if I call on you.
Yeah, exactly. It's just up for the remainder of the episode. Is particle accelerators how we also discovered quarks? Or is that something different? Am I misremembering that?
No, you are correct.
Okay, cool.
Yeah, I get into a little bit about what we've discovered using particle accelerators near the end of this episode.
Okay.
But yes, we have discovered so many things about our universe, the subatomic universe.
Quantum mania, if you will.
Quantum mania. Wow! From particle accelerators.
Got it. Okay. Oh, God, this is going to be such a nerdy episode.
Get ready. I parsed it down a lot so I don't have to like teach.
Sure, like fundamental physics.
Yeah. I don't have like a dry erase board that I'm going to pull down.
I really want like all of a sudden like we have a projector screen we pull down and it's like 1962 like wide frame glasses, a pointer. Bad
we cut
music.
To us being in an old university.
Black and white. Yeah, exactly. We'll do that one day.
The wonders of nuclear physics.
Truly. That should open this episode. It is just Batman.
Yeah. All right, so we have our medical uses. We also have some uses environmentally speaking. These beams can be used to detect chemical elements in air, water, and soil samples. So like when the EPA takes samples in your neighborhood or around wherever, you can use these accelerators to detect what is potentially poisoning the air or whatnot. You know, fun stuff. In the industrial realm, sometimes blasting material with particles can make a material more durable, which is kind of surprising. Or whatever the company might need from blasting a material with particles.
Sure.
And then also they can be used to manufacturing of computer chips.
Okay.
And then something that I didn't even think about were security forces. They can use accelerators to help with cargo inspection. materials characterization, and other matters of national security. So like they can use a particle. So particle accelerators don't have to be these massive, giant, kilometer-long rings.
Sure.
They can be as small as I get into like the smallest one a little bit, but they can be handheld almost.
Oh, okay.
If you need them to be, like X-ray machines and whatnot.
Is a type of a particle accelerator, or like it's an offshoot?
I think certain X-ray machines are particle accelerators. Not every X-ray machine is a particle accelerator.
Right. Not every spectrum.
Exactly. Yeah. So like they can use accelerator to determine like, oh, does this thing have like radioactive material in it, or does this have like like just like the EPA would use to analyze soil samples, security could use it to analyze your cargo.
Got it. Okay.
That kind of stuff.
I'm there.
And we get to learn so much about the stuff that makes up our universe in a controlled environment by using particle accelerators. That's probably, and I'm going to say probably, definitely the main use and reason for these accelerators.
Okay, heard.
So finally, we get to how. I know. You've been waiting for it.
Tip of my tongue.
How do we get particles to accelerate that fast? Mm-hmm. So, while accelerators can vary in size and shape, they all have the same 4 components.
Oh, okay.
4, like bing, bing, bing. Yeah.
Bing. Yeah.
1, a source which produces the charged particles.
Okay.
2, a device that adds energy to the particles and speeds them up with static or oscillating electric field.
Okay.
3, the runway for the particle to travel down. The tube, that's usually the tube aspect of it.
Sure.
This tube is in a vacuum, so the charged particle doesn't hit any air molecules or dust and fuck up your experiment.
Okay.
And 4, you need electromagnets to steer and focus the beam of particles.
Fair.
Because like, how else are they going to go around the bend of a circular accelerator?
Right.
They'll just crash into your wall, and that's the end of that.
Now, do you think, would they bounce off? Like, if it was, let's say you didn't have the electromagnetics and you shot it down a tube and there's the curvature, would it hit and stop, or would it hit and bounce?
I believe it would hit and... So there needs to be a transfer of energy somewhere. So it might bounce off or break apart depending on what you're using.
Okay.
And then like whatever breaks off would bounce away. Kind of like if you threw a rock really hard against another wall and then the splinters shatter around kind of deal.
Okay. But it wouldn't stay intact and kind of like bounce its way through the rest of the...
Yeah, it wouldn't pinball around.
Right.
Yeah,
okay.
Eventually, unless like you're able to constantly energize it while it's still going around, it just wouldn't be as controlled as you need it to be. It wouldn't hit the target that you need it to.
Fair. Okay.
Electromagnets to steer and focus the beam particles. And before you ask, because I know you have another question at the tip of your tongue.
It's a whole scroll of them.
I'm going to tell you the largest and smallest accelerators out there.
Okay, cool.
The largest accelerator, as you probably know, you mentioned it already, is the Large Hadron Collider, the LHC for short, located at CERN, with a circumference of nearly 27 kilometers, or 16.8 miles.
Bananas.
Huge. The smallest accelerator is the Nanophotonic Electron Accelerator, shortened to NEA, located at the Friedrich Alexander University, Germany, I believe.
Okay.
And is 54 million times shorter than the LHC, approximately 0.5 millimeters, or 0.02 inches long.
What's the purpose of how small it is?
That is a great question. 1 second. I really like that question. Hold on.
We're pausing.
So I really like that question. I had to do a quick Google to get back to that topic. And from an article of space.com that was published on October 29th, 2023. From that article, it states that it was recently fired up. So I think they're kind of still fired up for the first time. So it was first used for the first time. And so I think they're just kind of still testing it and figuring out what it could do, but also according to this article, the scientists are thinking of all the different applications that you could have for this tiny accelerator, including using it inside human patients for cancer treatments or whatever else.
Oh, interesting.
Yeah. So I'm glad we looked that up because that was a really good question.
As in, okay, so I guess I'm trying to conceptualize like how small 0.02 inches is.
A small coin.
Oh.
Like they have a picture of it on their article, and I'm not sure which euro it is, but it's a tiny ass euro coin.
Sure. Similar to like a dime or maybe like a penny.
Yeah, I'd say.
Okay. Because I could swallow a penny. You know what I mean?
Yeah.
So
I'm pretty sure either I did or my brother did when we were kids. So,
but I think about that. That's actually interesting that you say that, because if I'm going through cancer treatment, like I wonder what that effect would have to kind of ingest that, and then as a doctor on the remote end of things, be able to activate, you know what I mean?
Yeah, I wonder if it would, rather than being ingested, it would be, you would have a robot holding on to this tiny piece of equipment
and kind of moving
and
over
going into your body to precisely blast, instead of a general blast on your cancer cells that could also hit.
They would find specific cancer
cells. Yeah, they might be able to find and target the evil cells.
Oh, I like that.
Yeah.
Okay.
So they're still trying to figure this out. So that what we just said is all conjecture.
100%. This entire show is all conjecture.
What should we conjecture?
Yeah.
So that's the potential uses for the nanophotonic electron accelerator. Again, abbreviated to NEA.
Very cool.
If you want to look into it more on your own time. Very exciting stuff. It's really cool. And a little bit more about how we get the particles to accelerate that fast, going back to that a little bit, is that there are straight tube ones, and then there are also giant circle ones.
Okay.
And the LHC, the Large Hadron Collider, at CERN are two giant loops intersecting almost like a Venn diagram.
Okay.
But not as drastic. It's more like an 8, I guess.
Okay.
But if we're using a loop-shaped accelerator, the particles will go around and around and around that loop until they are sufficiently energized. And then either they will send that particle to hit its target, like they'll insert I don't know the exact mechanics of it, but they have a system where you have one particle going around the other way, the other going clockwise, the other going counterclockwise, and then they're able to essentially pull a hatch out, and then
they'll meet.
They'll collide.
Okay, so that's what I was thinking too. It's almost like the wrong way to make an 8, where it's like two circles, but they have that connection point. You know what I mean? Yeah. Because everybody knows that an 8 is all connected. That's how you write an 8. But that makes sense, and that's what I was thinking, is that overlapping point more so than connected loops.
Yeah. Because with those electromagnets that they use to control it to go around the loop, they can use those magnets to steer the particle to collide it with its target.
Okay. And then you might get to this, but how quickly do they shoot them?
Close to the speed of light.
Oh, right. We said that already.
No. Okay. It's okay. Because we aren't able to travel faster than the speed of light, but we can get close.
Correct. You haven't watched Three Body Problem yet, have you?
No, I haven't.
Damn. There's and it's not really spoilers because whatever, but there's a point where they try to get to the speed of light.
Yeah.
And this physicist comes up with a theory of being able to get to 0.112%.
Oh, wow.
Of the speed of light. And they use nuclear propulsion in space.
Oh.
So basically they set it out, set this rocket out, and then create kind of this shield, right? So then it's here's the shuttle, and then here's this kind of ballooned solar shield connected to it, parachute almost, and then the nuclear kind of reactor would pass through the shield in like this little hole, explode, and then that nuclear propulsion would keep it moving. And as it kind of arcs and hits those different nuclear points, it would then eventually get to 0.112% of the speed of light.
Wow, that's interesting.
Should we try it?
Sure.
With all the money we have.
Yeah. Let's take a loan out real quick.
Yeah, and all the nuclear propulsion we have.
All this loose uranium I have.
Start pouring it onto the table. Yeah.
But regardless of shape, the tube or the circular version of the accelerator, once energized, the particle, like we said, collides with its target, and something close to magic happens.
Ooh.
The original concept for the particle accelerator came about during the early 20th century. So we're going to go back to a little history. Okay. We'll leave you thinking about the magic for a little later.
I'm thinking.
Trying to keep you in the story. So 1905, we got this guy, he might be famous, Einstein, published his famous E=mc².
Of course.
And the world loses their mind.
Truly.
This is all about his theory of relativity, stuff like that. So physicists in the early 20th century, especially after 1905, were excited to learn about the properties of atomic nuclei and subatomic particles. I wonder why at the time. World War II.
Go check out some other episodes we've done. Yeah.
We have an whole Oppenheimer one. Yeah. You go listen to that one. So up until 1932, scientists were really only able to measure the reaction between a nitrogen nucleus and an alpha particle. An alpha particle being a positively charged particle ejected spontaneously from the nuclei of some radioactive elements.
Got it. Okay.
There's going to be a lot of textbook definitions, and I'm sorry. I'm trying to keep this as lively of a story as possible.
You're good. It's very scientific.
It's heavy physics going on. So these particles that they were able to use at the time also only had kinetic energy levels as high as 8 mega electron volts, or MeV, which is 1 × 10 to the 6th power electron volts.
Okay. So a lot or a little?
Relative to what we can do today, tiny.
Okay.
It wasn't as high as they needed to be able to produce the experiments that they wanted to do.
Got it.
But Ernest Rutherford, if you had to guess, he's a British physicist with a name like Rutherford.
Guess a nationality, yeah.
So Ernest Rutherford believed that if they wanted to observe heavier nuclei getting wrecked by alpha particles, they would need to be able to add a lot more energy, so way more than the 8 mega electron volts, to these particles than they are giving off naturally.
Okay.
So we need to artificially boost them.
Sure.
And no one thought this was really possible until in 1928, George Gamow, Gamow, he was a Russian-born American nuclear physicist studying at a university in Germany at the time. So a man of the world,
if you will,
came up with a solution. He had a very simple idea, and he did some calculations for it. And he was like, let's just use less energetic ions. And with those calculations, this sparked the development of accelerators that could shoot a beam of particles suitable for nuclear research.
Okay.
What that all means, he wanted to use like more of the parts of the atom rather than the whole ass atom.
Got it. Okay. Got it. You're being strategic about what you're using to be able to get a more tailored result.
Yes.
Got
it. So he has those calculations. Everyone's excited, like, oh, shit. No, duh. Let's do it. Let's try to figure this out.
Clearly, that's the answer.
And now a lot of science and a lot of scientists worldwide worked on designing and improving the idea of the particle accelerator.
Okay.
at this point, we're able to reach energy levels of at least 25 MeV, which is a great improvement at the time. Nearly over tripling what we were able to get naturally.
Yeah.
And I don't want to demote the work or like think less of any of the work by not mentioning the folks that worked on all of this and all of their work.
Yeah.
But for the sake of everyone here and myself and you, I'm going to skip over a lot of the development.
Fair.
That being said, I would like to mention Donald W. Kirst. Kerst.
Okay.
So 1940, Donald constructs the first Betatron at the University of Illinois at Urbana-Champaign.
Oh dang! U of I, baby. Another Illinois university being involved in some sort of atomic
nuclear research.
Yeah, exactly.
Yeah. So a Betatron is an electromagnetic induction accelerator of electrons, or a type of particle accelerator.
Okay.
Reaching energy levels of 2.3 MeV. So this was his first one that he made. He was like, I think I have an idea for it. I'm going to build it on a small scale. And he was able to get it to 2.3 MeV.
Okay.
Eventually, he built more Betatrons of increasing energy with a 340 MeV machine being completed in 1950.
Dang.
Right. So he was like, I have this idea. Yeah. Let's see if it works.
So when did he start doing it? Sorry.
1940. So within 10 years.
Yeah.
And this was just coming up with the idea from George Gamow, the Russian-born American nuclear physicist studying at a university in Germany at the time, in 1928. So
his full title, if you will, please.
Exactly. So now by 1950, he was able to create something up to 340 MeV.
Okay.
Yes.
Okay. Do we know if any of his research influenced the work at like Los Alamos or things like that during the war? Or is it kind of just an assumption of maybe?
I believe everything around this time of science is connected.
Got it. Okay. That makes sense.
Yeah, because like I have this topic and like other topics I've researched, everything I felt like Charlie from Always Sunny, where like I was researching, I was like, that motherfucker's involved too, like, oh, it's part of this, and like I just had red string all over my office at work, and I was like, this is insane. And I was just like, let me tell you about this.
Just going mad.
Right. Yeah. So I'm gonna say 95% yes.
Okay.
That this research done on the particle accelerator is also influencing, or at least helping, the research of Oppenheimer and the nuclear bomb.
Right.
It's like Einstein that was involved with all of this shit.
That's fair. Like, yeah, that's true.
It's all there. The science is there to help
support. Right. Exactly. In any way, small or big. Yeah.
Right. So once World War II ended, so a little bit before, Donald was able to get his machine up to 340. He was still increasing it exponentially throughout his development. But once World War II ended, we have Edwin Madison McMillan at Berkeley. Mm-hmm. That's one guy. And then we also have, and my Russian still hasn't improved, and we have Vladimir Iosovich Wechsler at Moscow independently came up with the principle of phase stability.
Okay.
So this is after the bombs have dropped. This is the start of the space race. Everyone's kind of cooperating slightly.
Sure.
A little. But like this is a big push for science.
I do love that after the bombs were dropped, we're like, don't look over there, look up, look to space. Right. Don't worry about what's happening.
Don't look about the rest of the bombs were dropping.
It's fine.
Where this is all research is happening, essentially. So they come up with this independently. They didn't share it. They weren't in communication.
Yeah.
They both came up with the principle of phase stability. And with this concept, you could maintain stable particle orbits in cyclic accelerators, breaking through a barrier on energy limitation. So before I believe they were just using tubes, straight tubes.
Oh, okay.
And so now we're able to use circle accelerators.
Yep.
Cyclic accelerators.
Mm-hmm.
And they were like, oh, if you use a circle, that particle can go around and around and around until it has enough energy. We're not limited by the length of the tube that you're using.
Right.
Because like you only have a limited amount of time within this tube before it reaches its max amount of energy. Because like even if you wanted to, like you can't bounce it back and forth. Because even if you think about like a swimmer doing laps, they get energy, but then they'll lose energy because they have to slow down, stop, turn around, and then try to boost back up to that acceleration level.
Right.
So like you only have one shot, like a gun. Pshoo. But now we have a circle accelerator, and it's like, oh, they can go around and around, keep building up energy. And so the phase stability made it possible to construct magnetic resonance accelerators for the electrons, and we called those synchrotrons.
Okay.
That's just what they were calling it.
Okay, got it.
It's just another type of particle accelerator, just very specific. So like the Large Hadron Collider is just the name of a type of particle accelerator. So like we could have smaller hadron colliders.
Got it.
I believe. I don't know if hadron is TM'd or not, but you could have something similar called a hadron collider.
Okay, I got you.
We still have betatrons. We have synchrotrons.
Got it.
And I always have to add that R in there because I forget about it. I think it's just synchrotron, but it's synchrotron.
Come on, Kevin.
So we get these cyclic accelerators, and progress is booming at this point.
Okay.
We're excited.
Very excited. Booming, booming, booming.
We're now experimenting using this new founded microwave technology developed during World War II for radar. We talked about this in our episode about SETI.
Yeah.
It's all fucking connected. To make our accelerators better. So we're using microwave technology to make our accelerators better. Larger and larger accelerators are being built since that was believed the only way to increase the energies of protons. So we're like, well, we need bigger accelerators to house this bigger equipment so we can charge the particles faster.
Right.
It's like how computers back in the day were like, oh, we need all this space, all this room to make the computer more powerful. But now
it's in your hand.
Yeah, exactly. But eventually, by 1952, Ernest D. Current and H.S. Snyder were able to demonstrate a technique of alternating gradient focusing or strong focusing.
Okay.
I get excited. It's the thing. Or strong focusing, which allowed the synchrotrons to only need magnets 1/100th of the size that they were previously required.
Oh, wow.
So we were able to really shrink down the magnets that we needed. Granted, we still needed big ones.
Sure.
As seen by the LHC, it's 27 kilometers.
Huge.
Right, it's huge. But this new development allowed future accelerators to be built at a more manageable size.
Sure.
So 1956, by 1956, Donald, the Betatron guy, thinks of a fun concept. He was like, hey, let's smash two moving particles into each other. You guys want to see some cool shit?
Donald's fucking hammered and like bourbon one night. He's like, let's just smash some shit. Why not make it particles?
Like him and his other scientist buddy are just like throwing beer bottles at each other, and they collide midair, and they're like, we should do that.
Particles.
Let's go. And they just toddle off.
Yeah. That's exactly what happened.
So Don, more eloquently, Don realizes, instead of just, that little bit, Don realizes through all of these new developments, the smaller magnets, the cyclic accelerators, that we should be able to observe the interaction of two particles moving in opposite directions colliding.
Okay.
This idea would require more than one accelerator loop.
Correct.
Called storage rings. So the two rings that make up the 8 are storage rings.
Got it.
And these rings would be used to independently accelerate the separate particles until they are ready to collide. So they're going to go round and round and round.
Right.
Get up the energy, and then they're going to smash. Smash. At this point, we have uncovered the technology to obtain the highest reaction energies possible. We are ready to really ramp up what we can do with these.
Okay.
So what happens when particles are accelerated and collide with something? What's that bit of magic that I mentioned earlier?
Oh, look at you.
Look at
a little
me.
callback.
The energy of the collision is transformed into matter in the form of new particles. Some of these particles, we believe, have even existed in the early stages of the known universe.
Okay.
So that's what we're trying to explore and find. Like, what's making everything up?
Sure.
How is this possible? As Sherlock famously said, mass energy equivalence, my dear Watson.
Yes.
I was really excited for that line.
Yeah, of course you were. I can see it all over your face. You love that.
I did. I was like, this is the nerdiest fucking thing I've wrote.
I didn't think you could get to a nerdy level in this episode, and you just layered it. Yeah.
So, mass energy equivalence. That little equation Einstein came up with in 1905 means that matter is just a concentrated form of energy, and the two are interchangeable. E equals mc squared,
right.
being energy, m is mass, c being the speed of light.
Right.
Interchangeable.
Yeah.
So let's talk about the 27-kilometer elephant in the room, the Large Hadron Collider. It's a little tight in the studio. So not only is the LHC the largest particle accelerator, but it's also the most powerful in the world.
Sure.
So like I said previously, by 1952 or around that time, we were able to, 1956. Around that time, we finally have all of the technology to be able to obtain the highest reaction energies possible. So now we have all of the concepts, all the ideas. Now we need to put it together.
Yeah.
Enter LHC. With this, the most powerful accelerator in the world, we are able to boost particles up to energies of tera electron volts, TeV.
Yeah. Okay.
This is 1 times 10 to the 12th electron volts. Before, the mega electron volts is 10 to the 6th power.
Oh, so we've doubled. Got it. I've always hated exponents, but I'm with you.
It's a fuck ton more.
Yes. Yes.
It's the difference between a million and a trillion, essentially.
Okay. Got it. I'm there.
So this massive and incredibly powerful accelerator is located at CERN, at the CERN complex in Geneva, Switzerland, 175 meters below the ground.
Oh.
It's all underground.
It's all underground?
It's really cool. Yeah.
Oh. I thought it was like up and about.
No.
Oh. No. I just imagined to get in, it's just like a little like outhouse sort of thing. And like, you like go in, it's like an
like, get smart.
Yeah. Exactly. Into the CERN labs.
That'd be, and there's just like a shepherd with like sheep and goats and cows, and he's like, huh.
There's like a line of scientists waiting to take their turn outside of a mountain. Yeah.
Incredible. I like that image. So the LHC had its first operational run started on November 20th, 2009.
Okay.
And this whole run wound up involving 284 collisions.
Oh, wow. Just in the first run?
Just in the first run.
How long is a run?
I have all the dates, and I'll go through those in a moment. But run 1, to answer your question right now, ran from 2009 to 2013.
Oh, wow.
Now, there are some brief pauses.
Sure.
During these runs, there have been 3. There are brief pauses to make adjustments.
Sure, of course.
Put in new particles, whatever. But like these runs go on for so long because it just takes a lot of energy.
Yeah.
It takes a lot to get the accelerator up to speed and whatnot, and there's just so many tests. Like, it's not just like one particle being shot; it is millions of particles being shot at once.
Got it.
So it's not just like two baseballs colliding. It's like a fuck ton of baseballs being thrown at each other.
Got it. I really only thought it was like two particles.
Yeah. For conversation's sake, it's way easier to say like one particle than like millions.
Okay, can I ask a basic physics question?
Yeah.
How do you isolate a particle?
That's a great question. It happens kind of naturally.
Okay.
In a sense of like when things decay.
Sure.
But isolating like one particle, not too. I don't know.
Because it's not like
that's not a basic physics
Tommy,
question.
Can you grab another particle out of the bag?
Yeah.
You know what I mean?
Oh, I forgot to order this one.
Right. Wilson doesn't come with like a container of particles. I
didn't know the answer off the top of my head, but I did a quick Google. As always, Reddit has the answer. And I'm going to credit the user, Robus et Celeritas on the r/ask Science subreddit. The question was posed, how are you able to isolate it? Because like particles are everywhere. Like how the fuck do you do that? And Robus said, quote, "We don't work with individual particles at a time. We create beams of many particles. The particles start in a source, which you usually heat up some material, maybe shoot microwaves at it, and then create a plasma. Once you've got it in a plasma form, you can manipulate it using electric fields to pull out particles of a certain charge, positive or negative. From then on, it's just guiding the beam around with electric at low energies and magnetic at high energies fields and accelerating them with electric fields." Does that make sense?
Yeah, I'm there.
Yeah. So essentially you create your soup and then you kind of guide your soup along the tubes.
Along the way. Okay. Can I ask another question?
Yeah.
Okay. And then we can
I hope I know the answer to this one.
We'll see. And this might be something I can't tell if it's dumb or not, so you let me know.
There's no such thing as a dumb question.
So we've clearly been able to turn mass into energy. Have we done the reverse?
Energy into mass?
Yeah, into matter.
Well, I don't know if we have, but based off of Einstein's E = mc squared, they are interchangeable.
Right.
So theoretically, yes.
Like I feel like in nature, sure. But
because like you can have a photon. Photons are an energy particle,
right?
But I believe they also have like mass and matter.
But like, can we build something out of just energy, like a physical like thing, tangible item just out of energy?
Yes and no. I'm going to say a lightning bolt. And the plasma that I mentioned earlier.
Okay, yeah.
It's not like blood plasma. It is similar soup, but it's not like I can feel the blood. But like lightning would be some type of like tangible energy.
Sure. But we haven't been able to like build like super, trivially, like a mug out of energy.
I don't think so.
Because this would because a lightning bolt is technically, yes, tangible. Like, nope, you can't grab it, but yes. But it's
Seems
not,
good.
It doesn't, son of a bitch. But it's not sustainable.
Correct.
So have we been able to create that? And that doesn't seem, not yet.
I don't know.
Because that would be interesting, because I think because then you could kind of just pull
energy
you're
around
God, you.
Then. Yeah.
To then build something
Yeah. I don't, I'm going to say no, but I don't know.
I think we walk over to Chicago and be like,
Hello,
can we test something?
Yeah. And we just sit in the...
It's like a 3D printer, but instead it's energy.
Right.
Okay, please continue.
Sorry. You're okay. So we had the first operational run, November 20th, 2009, involved 284 collisions. That's where we left off. Through these experiments, the LHC has helped us discover fundamental features of the universe previously unknown, including, but certainly not limited to, the Higgs boson, which probably deserves its own episode. It has been dubbed the God particle.
Yes.
We've also discovered...
You seem very upset about what has been dubbed.
No, I'm okay with it being called the God particle.
The God particle.
No, I mean, it's a very fancy name,
sure,
but like it's fine. So we have the Higgs boson, tetraquarks, We also had the first artificial creation of quark-gluon plasma. And this, I had to look up, is the densest form of matter outside of a black hole.
Oh, wow.
And this plasma supposedly existed in the early universe. We've also, with the LHC, refined the scope of searching for signs of supersymmetry, which also means we've challenged we've challenged the validity of the existing models through certain observations made. Supersymmetry being just like, it's kind of within its name of like things being symmetrical, like things that shouldn't be symmetrical are symmetrical.
Okay.
And then also we've made observations of coordinated motion at the subatomic level when it should have all been random. So when things followed a pattern when it should have just been
all over the
willy-nilly.
place. Interesting. Okay.
Which I believe is related. That bullet is related to the quark-gluon plasma.
Okay.
Or quark soup, as it has been lovingly called.
Love it.
But I'm not quite certain. Some of this stuff, some of the discoveries went way over my head.
Sure, yeah. It's fair.
It's really fascinating. I'm like, what the fuck is that? Like, there was a lot of like Greek letters involved, and I was like, this is not what I'm
That's like chalkboards and chalkboards and chalkboards.
Yeah, that's the black and white pull down thing.
Right. Exactly.
So like I mentioned before, since its debut, there have been 3 different operational runs. Run 1 being from 2009 to 2013. Run 2 being from 2015 to 2018. And then run 3 actually started on April 22nd, 2022, and is expected to continue until 2026.
Oh, wow.
So we still got one going right now.
We're in the middle of it.
We're in it. And between these runs, kind of like I mentioned a little bit that there were pauses during the runs, but the long shutdowns in between each run are used for repairs, upgrades, data collection, and data analyzing. Because you're just getting millions and millions of points of data from these runs.
Yeah.
And then between each run, you need to analyze all that. You need to see what we discovered, what happened during this run.
Right.
What we could do differently the next time, etc. So that's why there's such long breaks. Also, it's expensive.
Yes.
So that's the LHC.
Okay.
And there's another particle accelerator that I'd love to give an honorable mention to.
Okay.
And it is the one we have here in Illinois.
Ooh.
The Tevatron, located at Fermi Lab outside of Batavia.
Interesting.
Now, this fella is no longer active due to the LHC being the big dog now. But up until the LHC was built and operational, the Tevatron was the highest energy particle collider in the world.
Dang.
We had that here right down the street.
That's pretty cool.
Really far down the street, but
I was like, quite a bit of ways.
Batavia's the next town over. What are you talking about? Now, this guy was only 6.28 meters in circumference, so like a quarter of the size-ish of the LHC. And even though it was smaller, it was still mighty and helped us confirm and or suggest the existence of several subatomic particles, including the discovery of the top quark in 1995. So this thing has been running for quite some time.
Yeah.
And then as well as laying the path for the LHC to discover the Higgs boson. Analyzing... We used the Tevatron and analyzed the data accumulated over the years since 2001. So we took 2001 till like 2007 or whenever the Higgs boson was discovered. Excuse me.
Yeah.
I don't remember when it was. Yes.
For all of our listeners, can you, when you get to a good point, remind us why the God particle, the Higgs boson, was such an incredible discovery?
I will try to do that briefly. I was like, the Higgs boson probably needs its whole ass episode, but I will give a brief explanation once I'm done with the Tevatron here in a moment.
Perfect.
So we were analyzing data collected since 2001, including around 500 trillion collisions. So we had years and years of data that the folks at Fermi raked through all around the world. I believe were looking at this data.
Yeah. And
the Tevatron narrowed the search for the Higgs boson.
Oh,
so they were like, it's not all the way here. It's somewhere in between this level.
Talk about setting you up for success.
Yeah. And then the LHC was like, great, now we know where to look.
Okay. Yeah.
And then they found it.
That's awesome.
So the Higgs boson.
Mm-hmm. And it's Higgs, right? Not Hicks?
Higgs.
That's like that.
Yeah. And then boson, boson. It's essentially, this is going to be a very short thing, like a sentence long. So the reason why it's called the God particle is because the Higgs boson is associated with a field. So like an electromagnetic field, for example, a field, which I believe is called the Higgs field, where the Higgs boson comes from. And it is called the God particle because at the beginning of the universe, when nothing really existed, no particles had mass, they were all just kind of zooming around at the speed of light. Things could only form, stars, planets, etc., could only form because they gained mass acquired from the Higgs field, the Higgs boson, the Higgs particle.
Got it. Okay.
So like it essentially was the spark, the thing that gave things oomph to be able to form.
Got it. Okay.
So we were able to gain mass, create stars, create planets, create life.
Big Bang equivalency.
Very involved in the Big Bang.
Got it. Okay. Perfect.
That was very simple, very
gorgeous.
There's so much into it, and a lot of high-level physics that goes into it.
Sure.
But that's as much as I could parse it down.
That's great. That's great. I just knew that we just kept on talking about it, and I was like, I just wonder if we need to like a quick.
No, we did. Yeah. We did, and that was a good question.
Okay, thank you.
So the Tevatron Batavia, it's great.
Awesome.
That's where we left off, and then we talked about the Higgs boson. And finally, so you may all sleep tonight.
Yes, thank you.
I know what you're thinking.
Mm-hmm.
No, particle accelerators cannot create sustainable black holes. I remember during one of the runs of the LHC, everyone was like, oh, black hole. And I think it was around the time of the Higgs boson being discovered. Sure. Everyone was like, fuck, like we're going to create a black hole in this middle of Switzerland and we're all going to die.
Correct.
No. Einstein's theory of relativity backs up the case of producing microscopic black holes at the LHC would be impossible.
Okay.
Some theorize that it would be possible to create such particles, but the same theories state that the particles would disintegrate immediately. They'd form and then collapse, giving the black hole no time to gather matter and destroy the Earth. So they won't have enough time to just suck everything up and grow. Yeah.
It's a theory question.
Okay. Well, and if everything that I just said doesn't convince you, the LHC cannot produce something as heavy as a black hole.
So sure.
It's just not powerful enough and not large enough to create something that with that much mass and density.
The question was, theoretically,
Yeah.
Could you even produce a black hole and sustain it at a controlled size?
No, because the purpose of not the purpose, but
Sure.
the behavior of a black hole. I'm going to say no. I could be wrong, but I'm going to say no because the behavior of a black hole is to absorb light and matter and suck it in and eat it.
Sure. So even like in a vacuum, because space is a vacuum, we still see that same behavior. So to do that in a planet or something of that sort is impossible.
I would say so.
Sure. Okay.
I think we would need something much larger, and like a factor more powerful than the LHC to be even consider creating an artificial black hole.
Sure. Okay. Heard.
Would be my guess. But who knows? We still have a run going of the LHC.
Yeah.
And with that still happening, I'm excited to see what we discover about our universe this time around. We might discover how to create black holes. I don't know. I think we're fucked if we do.
I was going to say, and then we just like fuck over humanity. Right, would not be surprised.
There we go. Bloop. So yeah, that's all you need to. Not all you need to know. There are so many more fun facts and things about particle accelerators. But that's all I'm going to say about particle accelerators.
Fair enough. Thank you.
Any remaining questions?
Let me think.
So many
questions. No, I'll leave it there. Thank you for appeasing my questions.
I think there's questions.
Okay, actually, last question.
Oh, yeah. I knew it.
What? Son of a bitch. So, didn't we use an accelerator? And maybe I'm misremembering, to test out the theory of time travel. We shot like photons or particles at a board and we're able to, wasn't that an experiment? And then we were able to say the theory of time travel is possible so long as, speed of light, blah, blah, blah. Or maybe I'm misremembering that experiment.
I'm not sure. I don't remember. Okay. I don't recall that experiment.
Okay.
It sounds like something we would be doing and saying that we can't, based off of this, we can't time travel because we can't go faster than the speed of light.
Right.
Because that would be really the only way.
Yeah. Okay. So that was my last question. So thanks for appeasing me.
And we can't, we can, but we can't do hyperdrive or warp drive, all the sci-fi stuff.
Right.
Because we can't go faster than the speed of light. We can get close to it.
But we can go faster than.
Right. Our engines aren't able to get that fast, but we can shoot particles that fast.
Got it. Yeah, those are all my questions. Thank you. As I often will just text them and random questions.
Yeah.
And we could just sit here all day and I'd be like, so this theory and this theory and this theory. But that's what I love about metaphysical philosophy, which I like that my philosophy combined with your scientific brain really just kind of gets a theory headwind going. And I appreciate that. That's all I got.
Well, thanks for I hope you're still sticking around. Everybody else, thanks for sticking around, thanks for listening, thanks for subscribing.
Yes.
If you have yet to see us on the internet, make sure you follow us at WDYK _podcast.
Yes.
And hit us up if you have any questions or topics that you'd like us to talk about, or fun facts that you like to share. I'd love to put them on the podcast. I love sharing facts.
Yeah.
I don't breathe when I get excited and share facts.
As we on the back end saw multiple times today.
Yeah. I just go release all the air from my lungs because I get so giddy about this nerd shit. So thanks for being here. Thanks for listening. Thanks, Nick, for talking to me about particle accelerators.
Thanks, Deb. Bye-bye.
Bye.